Welcome to Learn with us. This is the 15th lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you solved some examples of shunt or parallel clipper circuits. In your previous lecture, you also studied about diodes in breakdown region, where you understood what are Zener diodes and how these Zener diodes are different from normal diodes. Now, what are the learning objectives of this lecture? In this lecture, you will understand the current voltage characteristic curve of Zener diodes. You will also study about states of Zener diodes and cases of Zener diodes. And in this lecture, you will also understand how you will find status of Zener diodes. It means you will understand how you are going to determine whether this Zener diode is in breakdown region or not with the help of some examples. Now we will understand the current voltage characteristic curve of Zener diodes. The Zener diode operates just like the normal diode when it is in the forward bias mode. As you can see here, it is behaving like a normal diode, and it has a turn-on voltage which is between 0.3 and 0.7 volts. However, when this Zener diode is connected in the reverse mode, which is usual in most of its applications, a small leakage current may flow. As you can see here, this is a small leakage current. As the reverse voltage increases to the predetermined breakdown voltage, it means up to this point, a current starts flowing through the diode, and this current is known as Zener current. Okay, this Zener current increases to a maximum value which is determined by the series resistor, after which it stabilizes and remains constant over a wide range of applied voltage. Now, in this graph, this Vz is the Zener voltage, which refers to reverse breakdown voltage. Okay, and here this Iz max is maximum current at this Zener voltage, whereas this Iz min is the minimum current which is required for the diode to break down. So this is the current voltage characteristic curve of Zener diodes. Now, just like normal diodes, there are two states of Zener diodes. One is conducting state or on state, and second is non-conducting state or off state. We know that this is the symbol of Zener diode, where this is cathode and this is anode. We also know that the Zener diode is employed in reverse bias condition. It means when this cathode is positive and this anode is negative. So when this Zener diode is on, then its equivalent circuit is like this, where this terminal is positive and this is negative, and here Vz is the voltage, and here again we have Vz. So this is Zener diode equivalent for on state, and when the Zener diode is off, then its equivalent circuit looks like this, and here we have voltage, this is positive, this is negative. Now when this Zener diode is off, this voltage is less than breakdown voltage, but it is greater than 0 volts. Okay, so these are Zener diode equivalents for the on and off states. There are two cases of Zener diodes. One is ideal case and second is practical case. First we will talk about ideal case. We know that this is a Zener diode, and since it is used in reverse breakdown region, it means this terminal is positive and this is negative. Now in ideal case, the constant voltage drop across the Zener diode is represented by a DC voltage symbol like this, where this is positive, this is negative, this is VC, so this is VC. Okay, so this is the ideal case of Zener diode, where this diode is behaving like a battery. Now what about practical case? In practical case, a resistor is connected in series with the constant voltage source like this. Here this is positive, this is negative, this is R, and this is Z, and here we have BZ. So this is the practical case of Zener diode, and the lower the value of this RZ, the more constant this VZ would be. Okay, it means the value of this resistor is controlling this voltage here in this practical case. Now there are two conditions. First is Zener at no load condition. In this case, the circuit will look like this, where this is positive, this is negative, and this is input supply voltage, and this terminal is positive, this is negative, this is a resistor which is connected in series. Now this terminal of Zener diode is positive, this is negative, and here voltage is Vz. For suppose here current Iz is flowing through this diode, and in this whole circuit current I is flowing, and since it is a series configuration and we know that in series configuration current remains same, it means here I is equal to Iz. Now second condition is Zener at load condition. Now in this case a load resistor is connected in parallel to this Zener diode like this. Okay, this is RL, here we have VZ, this is positive, this is negative, this is positive, this is negative. For suppose here current IR is flowing and here we have current IZ, this is resistor, this terminal is positive, this is negative, this is positive, this is negative, and this is VI. Okay, this condition is also known as Zener with shunt resistance. Okay, and if we look at this node and if we call it node A, and here for suppose current IT is flowing. Now if we look at this node A and if we apply KCL here, which is Kirchhoff's current law, we know that according to this law, the sum of currents entering the node is equal to the sum of currents leaving the node. Here only one current is entering, which is IT, and two currents are leaving. One is IZ and other is IR. We know that from Ohm's law V is equal to IR. So I is equal to V upon R. Now if we look at this IT, it is flowing here in this loop, and we can say that here at this node voltage is Vz. So in order to find this IT, we can write Vi minus Vz divided by Rs, because in this resistor the voltage drop will be Vi minus Vz. Okay, and here we have Iz. Now what about IR? We know that I is V upon R, and if here voltage drop is VL, we can also call it load voltage. So here this IR is equal to VL divided by RL. Okay, so this is the condition of Zener when a load resistor is connected in parallel. Okay, now look at this example. If you have a circuit like this, where this is a Zener diode, and as you can see here, the Zener is at no load condition. This is plus minus Vn, and for suppose here it is of 10 volts, and this is Rs, this is positive negative, and if its value is 0.5 kilo ohms, here current Iz is flowing, and here we have voltage Vz, and for suppose it is 6.8 volts here. So how you are going to find current in this circuit? Again, we can use KVL here. So our KVL equation will be, if we start from this point, our equation will be minus V in plus VR, because here we assume that the voltage drop across this resistor is VR, plus Vz is equal to 0, and according to Ohm's law, V is equal to IR. So here this VR is equal to IRS, because here current I is flowing in this circuit. So it means now this equation will look like this. Okay, and if we rearrange this equation, we get IRS is equal to V in minus Vz, and here this current will be equal to V in minus Vz divided by Rs. So if we put values here, and after solving this, we get I is equal to 6.4 milliamperes. Okay, since it is a series configuration, it means here I is equal to Iz is equal to 6.4 milliamperes. Okay, so this is your answer. Now here is your class task. If you have a circuit like this, where the Zener is at no load condition, and here current Iz is flowing, and for suppose here the range of this input voltage is from 20 to 40 volts, and this is Rs, and its value is 820 ohms. And if we assume that the Zener is in breakdown region and it has a voltage of 10 volts, then how you are going to find minimum current and maximum current? Here again you will use the formula V in minus Vz divided by Rs. For minimum current, this V in will be 20 volts, and for maximum current this V in will be 40 volts. So you just have to put these values in this formula, and then you will get these answers. Okay, here this is I, and we know that I is equal to Iz in series configuration. Okay, now how you are going to check status of Zener diode? It means how you are going to check whether this Zener diode is in breakdown region or not. you will follow some steps. First, you will remove this Zener diode from the circuit. Second, you will find the voltage across the load resistor, and if this load voltage is greater than Zener voltage, which is given, then the Zener diode is in breakdown region, and if this load voltage is less than Zener voltage, it means then the Zener diode is not in the breakdown region. Now, if you have a circuit like this, where this is a Zener diode, and here in parallel we have a load resistor. This is RL, this is RS, this is Vin, this is plus minus, this is plus minus, and here we have Vz, and here we have VL. Okay. Now after checking the status of this Zener diode, if it is found to be in breakdown region, it means when this VL is greater than Vz, then the Zener diode is said to be in on state, and in this case the circuit will look like this. Okay, this is RL, this is Vz plus minus RS plus minus Vin, because we know that this is the Zener diode equivalent for on state. Now if this Zener diode is not found to be in breakdown region, it means when this VL is less than Vz, then this Zener diode is said to be in off state, and in this case this circuit will look like this, where this is RL, this is V plus minus, this is RS plus minus Vn, because we know that this is the Zener diode equivalent for off state. Okay. Now look at this example. If you have a circuit like this, and here in parallel we have a load resistor RL. If this RL is of 1 kilo ohms, and this is positive, this is negative, and if this RS is of 320 ohms, and here current IZ is flowing, here current IL is flowing, here voltage is VL, and if Zener voltage is 10 volts, and here we have input voltage, if it is 20 volts, then how you are going to determine the status of the Zener diode, and how you are going to find unknown currents here. This IT is flowing here in this loop. Okay. Now first we will find the status of this Zener diode, that whether it is in breakdown region or not. For this, first we will remove this Zener diode from this circuit. Now this circuit will look like this, where this is RL, this is RS, and this is Vin. Now we will find load voltage VL, and its formula will be RL divided by RS plus RL, and this term is multiplied by input voltage, because we know that this VL is voltage across this load resistor RL, so this RL is written here in numerator. Now we'll put values here. We know that this RL is 1 kilo ohms, this RS is 320 ohms, and again here this RL is 1 kilo ohms, and here this Vin is 20 volts. Now after solving this, we'll get VL is equal to 15.15 volts. Now as you can see, this VL is greater than Vz, which is 10 volts. It means here this Zener diode is in breakdown region. It means it is on. So now this circuit will look like this, okay, where here we have RL, here is IL, here we have VL, here we have VZ plus minus IZ, and here we have Vin plus minus, this is RS. Here current IT is flowing. Now how you are going to find current IT? We know that at this point voltage is Vz, so this IT will be equal to Vin minus Vz divided by Rs. Now we know that Vin is 20, this Vz is 10, and this Rs is 320 ohms. It means now this IT is 31.25 milliamperes. Now we will find IL. We know that this IL is equal to VL divided by RL, and we know that this VL is in parallel with this VZ. It means this VZ is equal to VL is equal to 10 volts, because we know that in parallel voltage remains same. So we put this value here, and we know that this RL is 1 kilo ohms. It means this IL is 10 milliamperes. Now we know that this IT is equal to IZ plus IL. It means this IZ is equal to IT minus IL. IT is 31.25 milliamperes and IL is 10 milliamperes. It means this IZ is equal to 21.25 milliamperes. So these are your unknown currents here. Okay. Now look at this example. If you have a circuit like this, and now this load resistor is connected in parallel here. This is RL plus minus, and if it is of 1.2 kilo ohms, here we have RS, which is 1 kilo ohms. This is input voltage, which is 16 volts, and here this is Zener voltage, and for suppose it is 10 volts. Here current IZ is flowing, here current IL is flowing, and here we have voltage VL, and in this loop we have current IT. Now for suppose if this is your circuit, then how you are going to determine whether this Zener voltage is in breakdown region or not, and how you are going to find these unknown currents here. Now first we will find whether the Zener diode is in breakdown region or not. For this, first we will remove this Zener diode from this circuit, and now the circuit will look like this, where this is RL, this is RS, and this is Vin. And now we will find load voltage using this formula. Okay, now after putting values here, we get 1.2k divided by 1k plus 1.2k, and this whole term is multiplied with 16. So here we will get this VL is equal to 8.73 volts. Now as you can see, this VL is less than VZ, which is 10 volts. It means here this Zener diode is not in breakdown region. It means it is off. So now this circuit will look like this. Okay, here we have RL, here we have RS, here we have V in, here we have V plus minus, here current is IZ, here current is IL, here current is IT. Okay, now since this diode is off, it means here there is no Zener current, so this IZ will be 0, okay, amperes. Now what about IT? We know that this IT is flowing here, okay. Now again, if we look at this branch, there is no voltage here now. It means now we have VL here. So now this formula will become V in minus VL divided by RS, which is equal to 16 minus 8.73 divided by 1K, and it will give us 7.27 milliamperes. Now what about IL? We know that IL is equal to VL divided by RL. Here VL is 8.73 and RL is 1.2 kilo ohms, and it will give us 7.27 milliamperes. As you can see, IT is equal to IL, and we can also prove this from this equation, because here we know that this IZ is 0. It means here this IT is equal to IL. Okay, so these are your unknown currents here. Now again, if we look at this circuit and if we remove this branch, then this circuit will look like this. It means now this is series configuration where current remains same. Okay, now look at this example. If you have a circuit like this, where we have a load resistor which is connected in parallel here, this is RL, and if it is 1.2 kilo ohms, this is positive, this is negative, this is RS, and it is of 1 kilo ohms, and here current IZ is flowing, and if this IZ is 60 milliamperes, and here current IL is flowing, and here we have VZ, which is equal to 20 volts. Here voltage is VL, and here current IT is flowing, and this is positive, this is negative. Then how you are going to find the range of this input voltage that will maintain this Zener diode in breakdown region? It means here we have to find the values of X and Y, and we can say that here we have variable input voltage and this load resistor is fixed. Okay, now first we will find this minimum value of input voltage. For this we will use this formula, and here we know that this VL is in parallel with this VZ, and we know that voltage remains same in parallel configuration. It means this VL is also 20 volts. So we will put values here. This RL is 1.2 kilo, this is 1 kilo plus 1.2 kilo, and here we have V in. Now after solving this, we will get V in is equal to 44 divided by 1.2, and it will give us 36.66 volts. So this is the minimum value of input voltage. Now for finding the maximum value, we'll use this equation. Here we know that this IT is equal to V in minus Vz divided by Rs, and here this Ic is 60 milliamperes, and here IL is equal to VL divided by RL. Now after putting values here, V in minus 20 divided by 1K is equal to 60 milliamperes plus 20 divided by 1.2 kilo. Now here we'll get V in minus 20 divided by 1K, and this is equal to 76.66 milliamperes. Now if we rearrange this equation, we will get 76.66 milliamperes multiplied by 1K plus 20. Now after solving this, we will get 96.66 volts. Okay, so this is the maximum value of input voltage. So this is why. So after putting these minimum and maximum values in this equation, we'll get 36.66 volts, and here we have 96.66 volts. It means for this range of input voltage, the Zener diode will be maintained at breakdown region. Okay. Now look at this example. If you have a circuit like this, where a load resistor is connected in parallel here, this is positive, this is negative, this is Rs, positive, negative. For suppose here it is of 1 kilo ohms. Here current Ic is flowing, and if this Ic is equal to 32 milliamperes, and here this Vz is 10 volts, and if this input voltage is 50 volts, then how you are going to find the range of this load resistor or shunt resistance if this Zener is in breakdown region? It means now in this case we have fixed input voltage and variable load resistor. Okay, so we have to find these values of x and y here. Again, for minimum value of load resistor, we will use this formula. VL is equal to RL divided by RS plus RL, and here we have V in. Here VL is equal to 10 volts because it is in parallel with Vz. So here we have 10, and here if we rearrange this equation, we get Rs plus RL is equal to RL 50. Okay, now if we put value of Rs here, we get 10K plus 10 RL is equal to 50 RL. Okay, and here if we rearrange it again, we'll get 50 RL minus 10 RL, and here this is 10K and it is equal to 40 RL. It means now this RL is equal to 10K divided by 40, and after solving this you will get 250 ohms. Okay, so this is the minimum value of shunt resistance. Now again, for finding the maximum value, we know that here current IL is flowing and here current is IT. So we will use the equation IT is equal to IC plus IL. This IT is V in minus Vz divided by Rs, and here this Iz is 32 milliamperes, and we know that this IL is equal to VL divided by RL. Okay, here this Vn is 50 and Vz is 10, Rs is 1K, and here we have 32 milliamperes. This VL is 10 and here this RL is unknown. Okay, so after solving this we'll get 40 milliamperes minus 32 milliamperes is equal to 10 divided by RL. It means here we'll get RL is equal to 10 divided by 8 milliamperes, and after solving this we will get RL is equal to 1250 ohms. In terms of kilo ohms, it is written as 1.25 kilo ohms. Okay, so now this is the value of phi. Now if we put the values of x and y here in this equation, because we know that this is the maximum value of shunt resistance. Okay, now this equation A will be 250 ohms, this is RL, and this is 1.25 kilo ohms. Okay, it means now for this range of shunt resistance or load resistor, the Zener diode will be maintained in the breakdown region. Okay, now look at this example. If you have a circuit like this, where we have a load resistor here, RL, and it is of 2 kilo ohms. This is Rs, which is of 0.5 kilo ohms. This is Zener diode, and here voltage is 6.8 volts. This is input voltage, which is of 20 volts. And for suppose if this Zener diode is practical, and here the value of resistor is 10 ohms, because we know that in case of practical Zener diode, the equivalent circuit looks like this. It means here a resistor is connected in series with this voltage source. Now if you want to find total Zener voltage at no load condition, and you want to find total Zener current under load condition. So how you are going to find these unknown values? First we will find total Zener voltage at no load condition. It means we have to remove this branch now, and if we replace this Zener diode with this practical equivalent circuit, then this circuit will look like this. Here we have 20 volts. This is RS, this is RZ, this is VZ, it is 0.5 K, it is 10 ohms, and it is 6.8 volts. Okay, so the total potential difference here in this circuit will be 20 volts minus 6.8 volts, means from this point to this point we get 13.2 volts. Okay, now if we want to find voltage across this resistor RZ, then if we call it VR, then by using VDR, its formula will be RZ divided by RZ plus RS. This term is multiplied by this potential difference V. So now if we put values here, we get 10 multiplied by 13.2 divided by 10 plus 0.5 K, and after solving this we get VR is equal to 0.259 volts. Okay, now we know that in practical diodes these two terms are making this Zener diode. It means now this total Zener voltage will be 6.8 volts plus 0.259 volts, which is equal to 7.06 volts. Okay, so this is total Zener voltage at no load condition. Now we will find total Zener current under load condition, and we know that the equation is IT is equal to IZ plus IL. Now we know that the formula of this IT is V in minus VZ divided by RS, and here we have this IZ, and we know that the formula of IL is VL divided by RL. Now we know that this VZ is 7.06 volts, and in case of parallel combination voltage remains same. It means under load condition VZ is equal to VL is equal to 7.06 volts. Now if we put values here, we get 20 minus 7.06 divided by 5K is equal to, sorry, this is 0.5K, is equal to IZ plus 7.06 divided by 2K. Okay, now after solving this equation, you will get IZ is equal to 22.35 milliamperes. Okay, so this is your Zener current under load condition. Okay, so these are your answers. Now that's all for today. What are the key takeaways of this lecture? In this lecture, you studied about states of Zener diodes, cases of Zener diodes, and You also understood how you are going to determine the status of Zener diode, like whether it is in breakdown region or not, and you also solved some circuits with Zener diodes.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.